Hi, everyone. Welcome and thank you for joining part 6 of the technique series on Zeta potential. My name is Julie Chen-Nguyen, and I'm going to facilitate today. Okay, so let me just take us through really quickly. This is part 6 of the series. The last one will be image analysis, but you can look at all the recorded webinars on our website. Okay, David, would you please go ahead and share your screen? I'm going to pass the ball to you.
So I want to thank Julie and HORIBA for inviting me to talk today about a concept that I was first introduced to in 1962 and have made measurements and use of since 1965 when I designed the prototype of what became the first successful commercial Zeta potential instrument. The title of my talk today is Zeta potential, a necessary parameter in formulation and applications of suspensions. And I'm going to meander through a few measurements culled throughout those 50 years. But first, let's start at the very beginning, as the song goes. Many manufacturing products involve either in the final state or at some stage of their production, suspensions of particulate materials. So we must first briefly discuss two fundamental parameters that control the nature and behavior of every system in which one phase is dispersed in another. The phases are distinguished by the terms disperse phase for the internal phase forming the particles, and the dispersion medium for the external fluid in which the particles are distributed. The two fundamental parameters are the extent of the interface of the dispersed phase and the interfacial chemistry of the dispersed phase, respectively. The physical nature of a dispersion depends on the respective roles of the constituent phases. And there are numerous examples, but today I'm going to focus only on the most widely formulated type of dispersion, that of particulate suspensions, solid in liquid. The physico-mechanical characteristics that constitute the interfacial extent can be summarized as the extent of the particle-fluid interface, which is characterized by properties such as the particle size and distribution, particle shape, morphology, surface area, the whether internal, external. The physico-chemical characteristics that constitute the interfacial chemistry are more complex, but the prime property is the surface charge that in turn depends on the type, number, and degree of ionization or association of any material surface functional groups in relation to the fluid chemical composition. While attendees may well be acquainted with the measurement of one or more members of the former group, unfortunately, the interfacial chemistry is often a neglected parameter, particularly in pharmaceutical and biomedical applications, even though the formulation of suspensions, it can be as significant as, and sometimes more so, than the interfacial extent. And through this presentation, I hope I can make that case. It is important to recognize that these two parameters are not strictly independent variables. For example, the extent of the interface can be modified by particle comminution, milling and grinding, which may expose new surfaces and hence alter the surface interfacial chemistry. Alternatively, a change in interfacial chemistry may be brought about by, say, adjustment of solution pH or addition of an electrolyte, which can result in particle aggregation, which in turn reduces the extent of exposed surface area. The influence of changes in these two parameters permeates every aspect of suspension formulation, manufacture, and testing. To talk about that, of course, is a separate topic for another day. Suffice to say that both parameters need to be measured. And HORIBA, of course, supply a variety of characterization instrumentation, including a device to measure Zeta potential, the SC100. Here endeth the sales pitch. The schematic on the left here, taken from my PhD thesis, is derived from a photograph of a sphere in a wind tunnel, but it does serve to illustrate the situation of a particle in a liquid. Note that the flow lines do not actually touch the surface of the particle. There's a boundary layer. Now, when a particle is placed in a liquid, the liquid wets the surface, and there is a boundary layer of a liquid around the particle, which is different from the bulk fluid. It has some structure to it. The liquid molecules absorbed at the interface have fewer degrees of rotational and translational motion, and ions and other moieties can be trapped. So we can see there's a solvated particle is different from a dry particle. By the way, this also explains why measurements of particle size using dynamic light scattering can often give results at odds with those from microscopy. If a particle moves, it takes this boundary layer with it. In reality, the thickness of this boundary layer is not well defined, which is why I show it as a sort of wavy line. The edge, however, on the outside edge is called the shear plane. Now, all particles, when placed in a liquid, will acquire a charge. I'm not going into the details on how and why. This surface charge will give rise to a surface or thermodynamic potential. That's it for the model and theory. But we can see that the Zeta potential is related to the true surface charge. But as the schematic shows, it is more precisely an empirical nonlinear relationship with the particle surface potential. But if the surface charge changes, then so will the Zeta potential. I like to call it the effectiveness of the surface charge in solution. Importantly, its measured value depends crucially on the exact constitution of the suspension liquid, such as pH, concentration of any ionic electrolytic moieties, and temperature. So actually, it's useless to quote a single Zeta potential value without specifying the suspension conditions. At the simplest level, the sign and magnitude of Zeta potential can help maintain a more consistent product, and at a more complex level, it can improve product quality and performance. At the very least, its measurement answers the question, is the electrical charge on the material positive or negative? This information is often enough to suggest further steps in formulation and processing. The next higher level inquiry has to do with quality control. Has the product sufficient electrostatic repulsion to maintain its stability? So, how do we measure Zeta potential? There are 4 ways in which the Zeta potential can be obtained. The techniques are all based on the presence of an electric double layer and the movement of a charged surface in relation to a liquid. The most widely adopted technique is that of microelectrophoresis. I call it micro to distinguish it from the analytical technique of gel electrophoresis, which of course uses exactly the same principle. It relies on measuring the movement of a charged surface in a stationary liquid by means of an applied electric field, and so is ideal for suspensions and is of course the basis for virtually all modern commercial devices, including the HORIBA SZ100. From microelectrophoresis, you obtain a parameter called the electrophoretic mobility, from which the Zeta potential is calculated using some appropriate theoretical model. I'm not going into any further details of the different electrophoretic models, or the techniques, or the various models used for the calculation. Now, I'm showing this slide about nanoparticle surface chemistry because there's an accelerating increase in interest in nanotechnology applications, especially in the pharmaceutical and healthcare industries. Now, nanoparticles are things that underpin the technology, but what we're really dealing with are colloids. And colloids are particles whose size, simplistically, is less than 1 micron. But as we see from this schematic, as the size decreases and gets smaller below a micron, more atoms and molecules that comprise the actual molecular structure of the material become surface moieties. And at 10 nanometers, it's 30%. A practical consequence is the increased relevance of surface charge effects. As we get smaller, what are normally negligible for massive solids, non-colloids, become dominant in the description of nanoparticle behavior. Crystal lattice defects, anisotropy, and impurities now become critical attributes. Measurement of Zeta potential of these materials now becomes vital. This shows a schematic, the effect of pH on particle charge. Possibly the most common practical application of Zeta potential measurement is in predicting and controlling dispersion stability of suspensions. A sufficiently high Zeta potential, whether positive or negative, say 20 millivolts or more, will usually confer long-term stability on a simple dispersed system. Conversely, a low Zeta potential, somewhere between 0 and possibly plus 5 millivolts, will often result in aggregation. As we will see, the surface charge of many materials, especially metal oxides, is very sensitive to solution pH, and a key to their dispersion behavior is the isoelectric point, the pH at which the Zeta potential is 0, as we can see from this schematic. but the plots can give us more information. At the IEP, a particle suspension will have no resistance to aggregation. Now, this is utilized in applications such as wastewater treatment, where a polyvalent ionic coagulant, such as alum, are used to remove unwanted suspended material. It also means that attempting to disperse materials in an IEP solution condition is an exercise in futility. But if the IEP is known, then the sign of Zeta can simply be determined from the solution pH. These plots are sort of functionally S-shaped, and we see that the magnitude of the Zeta increases either side of the isoelectric point, but eventually plateaus at extremes of pH range. This is the condition of maximum dissociation or ionization of any surface functional groups and will provide, of course, maximum electrostatic stability. It can also be used to great effect when dispersing particles, because the greater the magnitude of the Zeta potential, the less is the need for any additional dispersing aid. Surfaces whose IEP is below pH 7 have acidic character, while those with an IEP above are basic in the sense of Lewis acid and bases. So the first order of business should always be to measure the Zeta potential versus pH profile for any material prior to use. And here I just show you some typical results. They would all run in an appropriate background electrolyte of a so-called indifferent electrolyte. I prefer to call it spectator electrolyte. It watches the game, but isn't truly indifferent. Sometimes it interacts, just like in a ball game itself. As an example is titanium dioxide. If it is manufactured by the hydrolysis of titanium tetrachloride, then the sodium or potassium chloride must be avoided, since chloride ions will specifically absorb, changing the Zeta potential profile, including the isoelectric point. It is much better to use sodium or potassium nitrate. Now, for many materials, the slope of the Zeta potential plot is quite steep, as we see here. In this range here, the pH itself must be controlled tightly, because any small changes in pH will make large differences in the Zeta potential. Personally, I prefer to work at pH values basically above 3 and below 10. This is because at extreme values, you can often get irreversible chemical reactions taking place. The table here just lists the isoelectric point for common oxides. These are average values meant only as a guide, and so should be used with reservation. However, I must stress that it's far better to measure it yourself. As we're going to see, the actual value will differ depending on the source from which the material has been obtained, the manufacturing or preparation method, any pre-treatment, subsequent purification processes, and the presence of impurities. The surface charge of ionic solids, such as metal halides, sulfates, and carbonates, can be changed by addition into solution of ions that make up the molecular crystal. So as an example here, let's take fluorite. Addition of as little as 10 to the minus 3 molar calcium ions to a dispersion of fluorite can effectively reduce the surface charge to 0. With barium sulfate, you get much different behavior and Zeta potential between using hydrochloric acid and sulfuric acid to change the pH, because the sulfate ion is basically specific to the barite. All of this, of course, can be checked and monitored using Zeta potential mixtures, which brings me to preparing mixed slurries. Since materials are charged and will have different isoelectric point values, then mixing suspensions of 2 or more can have unwanted consequences. Let's take an example of making lead zirconate titanate, which uses lead oxide, titanium dioxide, and zirconia. We can see from the table that at all pH values then, between pH 4 and 11, a mixed slurry will be unstable and the various materials will be massively heterocoagulated. The degree of aggregation and the structure created will be different depending on the specific pH between 4 and 11. This will impact the sintering, of course, of any slurry of those mixed oxides. Of course, you can always get a good dispersion at both lower and higher pHs. But this is not always an option. The best way then to prepare a mixed slurry is to use a dispersing agent, but that's also a topic for another day. Carbon blacks, often produced by the thermal dehydrogenation of hydrocarbons, such as residual oil left after catalytic fractionation of crude oil. Okay, so what happens is, because this is a natural product, they can contain significant amount of heteroatoms, hydrogen, oxygen, sulfur, nitrogen, bonded to the polyaromatic layers. So the surface chemical properties of the carbon black are determined by the type, number, and distribution of these functional groups, and as can be seen for this figure, they generally fall into one or two groupings, depending upon the relative proportions of those functional groups. Acidic carbon blacks typically have an isoelectric point somewhere between 3 and 4, while basic blacks have an IEP in the range of 8 to 10. The acid-base characteristics are strongly dependent on the oxygen content, which can be varied during manufacture and by various after treatments. In different applications, carbon blacks are dispersed in either water or solvents. The more oxygen groups, the more acidic the surface, and the easier it is to disperse carbon black in water. But it will make it more difficult to disperse in a non-polar solvent, in which case there will be a need to use a dispersing aid, or better still, use a basic carbon black. Zeta potential measurements, as we can see, can be used to characterize the surface chemical nature of carbon black and so enable optimum selection of an appropriate black for a given application. Further, as I've said, the greater the magnitude of the Zeta potential, the less is the need for any dispersing aids. So let's look at oxides because they're used a lot. While materials can be manufactured in some cases to a precise particle size, it's difficult, if not impossible, to obtain a constant surface charge. Post-manufacture, of course, can help. Milling, as I've said, which breaks down aggregates, exposes fresh surface, may not have the same chemical characteristics. An extreme example of this is coal. If you break a piece apart, one face can be bituminous and the other anthracitic. Industrial materials are never 100% pure. They contain impurities which can and do alter the surface charge. And the impurity can be electrolytic debris left over from the manufacturing process. Simple test here. Take a sample, shake it up in distilled deionized water, let it settle, measure the conductance. You'll see that there's a huge amount of debris left over for industrial materials. Most crystal lattices, as I've already said, are anisotropic, and this results in surface defects, and in the case of metal oxides, provides the amphoteric hydroxyl groups that now undergo reaction with either H+ or OH-. Importantly, the oxides of most di and tri metals are amphoteric, and dissolution tends to be in the form of the hydroxide. Swings in pH can cause reprecipitation back onto the oxide surface in a different chemical form, altering the surface chemistry and hence the charge and hence the Zeta potential. Natural materials such as clays are aluminosilicates, in which the negative charge is developed because the difference in valence between the Al3+ and the Si4+ ions in the crystal structure. For natural materials, you get what's called isomorphic substitution, with varying proportions of minor elements, manganese, nickel, copper, you name it itself. So the net charge of any clay depends crucially on its prehistory, and care must be taken in formulation when using clays. It might not be possible to substitute or replace a specific clay from a given manufacturer with another. Silicate is another very, very widely used material. The surface properties of the silicate depend on how it is being manufactured, whether synthetically or natural. And they range from strongly hydrophilic on this side because of the silanol groups to strongly hydrophobic because of the siloxane groups. Typical silicas are somewhere in the middle itself. The properties there will depend then on what type of surface groups are present, as well as their ratios, and crucially, how long the materials have been dispersed in water. A simple experiment: take a silica powder, heat it in an oven, let it cool, put it in water, measure the Zeta potential. Then measure it after 24 hours. It can often take more than 24 hours to attain a true equilibrium and a constant zeta potential. This needs to be checked for any silicas. And here's an example of two sets of data from two different manufacturers, supposedly equivalent, one in the US, one in the EU. Each pair has been subjected to two different surface heat treatments, and the zeta potential, as we see, can easily differentiate between them. However, it is quite clear that the two treatments cannot be the same. The materials from manufacturer one are clearly less hydrophilic, and there's very little difference in the zeta potential, but there's a massive shift in the isoelectric point. Those from manufacturer two differ in magnitude quite a lot in the zeta potential because of the different number of surface solenoid groups and their ability to dissociate. Thus, any surface modification needs to be checked. It should never be assumed that similar materials from different suppliers will be isocratic equivalent. An assumption of zeta potential uniformity for a material can have unwanted consequences in formulation. So let's look a little bit closer at surface modification. Many materials have special coatings to allow for better wetting, dispersibility, and processing in different media, water, oils, solvents, and even polymer melts. And we just show here the type of modifications you can find for titanium dioxide. But note, it's not always obvious from the packaging. Here, I'm showing examples of a rutile titanium labeled as Ti pure rutile, coated from the MSDS with different ratios of silica to alumina. But let's look at R900 here, this one here. What we see from the analysis is this material here is coated only with alumina, and so has a zeta potential closely relating that for a pure alumina. So as far as formulation is concerned, this material needs to be treated chemically more like alumina. The R931 has been shifted in the opposite direction towards silica, and therefore has to be coated, has to be treated more like a silica. But note from the analysis that it contains equal amounts, apparently, of the silica to alumina. This suggests that the titanium was possibly coated first with alumina and then overcoated with the silica. The R960 in the middle, if we notice this graph here, has an isoelectric point somewhere just around 5 or 6, and it looks very similar, if you recall, to the profile that was obtained for a pure titanium dioxide, if you've called back in slide 8. But because we look at here and we see that we have silica and alumina on the surface, then what we're finding is that these two basically oxides are both present on the surface, and it's the balance between the two. And since it's shifted south of 7 down towards 6, it says that yes, we've got more silica on the surface than the alumina. So this demonstrates that the bulk percentages found from the MSDS or technical data sheets determined from elemental analysis are not always a reliable indicator of how the surface would actually behave in solution. So again, it's critical to check the Zeta pH profile for oxides before use. Now, it shouldn't be assumed that different lots or batches of the same material will necessarily have the same profile or even the same isoelectric point, since I've already said, it's difficult, if not impossible, to control the process precisely. And here I show data collected over a 5-year period and the isoelectric point of the same grade of rutile, and we see it varies by almost 2 pH units. The implications of this to dispersion technology are obvious. Once again, the incoming materials need to be checked for their pH. Silicon carbide and silicon nitride are used for a whole host of reasons, but if pure, they should be hydrophobic and difficult to wet in water. However, surface hydroxyl impurities will impart sufficient hydrophilicity such that a zeta potential profile can be attained, as seen in these two plots. So this silicon nitride basically will wet in water quite well, which means it won't wet very well in a non-polar solvent. Polymer latexes are used in a wide variety of applications, and a common method of industrial production is by emulsion polymerization. The final latex particles stabilized by sulfates and carboxylic groups, which are chemically part of the polymer surface, resulting from the initiator, used in the reaction. In addition, there will be physically adsorbed surfactant molecules from the emulsifier, which have polar groups anionic or non-ionic. The final product is always contaminated with unwanted byproducts, unreacted monomer, oligomers, electrolytic debris, etc. from the reaction. The latex is usually subject to some sort of cleaning process, such as steam stripping or ion exchange, but it is not extensive. We're not talking about NAST traceable standards here. Further, industrial latexes are often stored for a long time before actual use, and they will age. You only need to open a container and smell the unreacted monomer that is diffused out from the inside of the latex particles, again, changing the surface functionality. So the ability of a latex to perform a given function, such as a binder, will depend on the surface chemistry prevailing at the time of use. The example I show here is for a sample of polyethyl acrylate, widely used as a plasticizer because the polymer is soft and can easily film form. The graph on the left shows measurements on a fresh sample, straight out the reactor, but nominally cleaned, compared with a sample that had been left to age over an extended time period, then extensively cleaned by serum replacement, which very efficiently removes all material not chemically bound to the surface, exposing, of course, the true nature of the chemical surface. The Zeta potential measurements show clearly a change in functional activity between the two latexes. At neutral pH, at this neutral pH roundabout here, there's very little difference in the Zeta potential, but at acid or basic media, there's large differences. So if you were only to make a single measurement at around pH 6, you would conclude, erroneously, that both these materials were the same. So the surface chemistry of the latex and hence its performance is very much dependent again upon the history of its production and storage. And this again can be monitored using Zeta potential. As I said, polymer latex is prepared by emulsion polymerization, but typically stabilized by an adsorbed layer of surfactant, which is utilized to control the particle size. Typically, this can provide a Zeta potential of around -40 to 50 millivolts in water, around pH 5 or 6. Having a high Zeta potential is, however, no guarantee that a suspension will be stable under all processing conditions. This is because Zeta potential measurements are made on quiescent systems, i.e. at rest. During formulation and production stages, many suspensions are often subject to shear by pumping or high-speed steering or heat, and this additional mechanical or thermal energy is oftentimes sufficient to promote aggregation. The stability of latexes can be enhanced, however, by addition post-manufacture of additional surfactant to a latex suspension. It may at first sight seem surprising that an anionic negatively charged species can adsorb onto a negatively charged surface, but this is because in many cases the latex surface is never fully occupied by the surfactant molecules during the polymerization reaction. And the graph on the right here is an industrial PEA latex that was extensively cleaned by serum replacement. The initial Zeta potential in millicube water at pH 5.6 was about -48 millivolts, and the latex was titrated with a linear long chain C1418 sulfonate, and the process followed directly using Zeta potential measurements. It's clear that the latex surface was not initially fully covered with surfactant. The final Zeta potential increased by almost 70% to -80 millivolts, which would provide much greater tolerance to mechanical and thermal action. There's great renewed interest in proteins, but it is important to know their isoelectric point, and I show some data for proteins adsorbed onto the surface of octyl sepharose beads. We can see that the Zeta potential profiles of the coated beads is completely different from the bare uncoated beads. So what we're measuring is the Zeta potential of these two proteins. Now, back when I was doing these measurements, I didn't have the luxury of modern instrumentation with high power lasers and sensitive photodiodelectors. These modern instruments can potentially measure proteins directly. But I show this because adsorption of chemicals onto particles is important. For example, proteins are adsorbed onto latexes and other carrier particles for use in immunoassay and related diagnostic testing. And it is critically important that the carrier surface be completely coated with protein, And as demonstrated in the last slide, this can be determined using zeta potential. Gelatin is a heterogeneous mixture of water-soluble proteins present in collagen, extracted by boiling skin, tendons, ligaments, etc. in water. Okay. The charge on the gelatin molecule and its isoelectric points are primarily due to the carboxyl, amino, and in some cases, the guanidino groups on the side chains. Factors such as molecular weight and number of functional groups impact the ionic characteristics of the gelatin. And the figure here shows 4 gelatins adsorbed onto PMMA beads. The zeta potential profile easily distinguishes between them. 3 of the gelatins here have an isoelectric point just around 5, a little bit less than 5 itself. They differ only in their molecular weight. Maximum dissociation, I said earlier, occurs at high pHs. In this case, above about pH 7, what we're seeing is we get maximum dissociation, excuse me, of the carboxyl groups on the surface of the gelatin. And the magnitude of zeta potential, which is telling us the number of carboxyl groups, increases with increasing molecular weight. And we can see that it's fairly quantitative. The Bloom number, by the way, is an indication of the strength of a gel formed from a solution of known gelatin concentration. It's determined using what's called a Bloom gelometer. And the Bloom number increases with increasing molecular weight, but also we can see trends with maximum negative zeta potential. This last sample here is a phthalated gelatin. The amino functions are neutralized with phthalic acid. The effect is to increase the negative character and shift the isoelectric point further to the acid side. A completely phthalated surface will always be negative. Interestingly, the amount of shift of IEP can be directly related to the degree of phthalation. So all the previous data I've shown was looking at materials. How can we put zeta potential to use in an application? Here, I'm going to look at a CMP, chemical mechanical polishing or planarization application, specifically to examine the effect of slurry fluid chemistry on the performance of a planar continuous glass polishing process. The table lists the results for just one type of commercially important silicate optical glass, a Corning 790 fused silica, for which the isoelectric point was found to be 3.5. The complete study also include borosilicate and dense flint glasses, but I'm going to show one example here for this one. 3 metal oxide polishing agents are used: a cerium oxide, a zirconia, and an alumina. And the table just shows the qualitative surface charge state of each material in acidic, neutral, basic water, determined from zeta potential measurements. As expected, the zeta potential of the polishing slurries varies with the solution pH and is either positive or negative depending on the metal oxide IEP. So we see zirconia at pH 10 is highly negative, and alumina at pH 4 is highly positive. Polishing experiments using a continuous polishing machine and a recirculating slurry, were carried out. And this graph simply shows the root mean square surface roughness values after 4 hours of polishing. The values were obtained using a non-contact optical profiler, and an average of 5 measurements were made for each data point. We can see that the surface roughness depends on the difference between the fluid pH and the isoelectric point of the polishing agents. And the smoothest surfaces were attained without exception in this positive half space here. This suggests that the fluid pH should always be larger than the isoelectric point of the polishing agent. Alternatively, a polishing agent should be selected whose isoelectric point is less than the pH of the fluid. This ensures that the polishing agent particles and the glass silica groups always have the same sign of surface charge. The corresponding repulsive electrostatic force then inhibits aggregation of the polishing agent particles and the dissolved silica species in the recirculated slurry. And the finely dispersed slurry remains so and hence produces the smoothest possible surface finishes. I'm now going to finish on a lighter note, preparing a Bayonet sauce. Making a Bayonet sauce from scratch is not easy, as anyone who's tried to make one can attest to. The recipe here is from the wife of an old colleague of mine. It basically comprises vinegar, egg yolks, and butter. You're essentially preparing or making an emulsion, and the egg yolk provides the emulsifiers. However, the idea is to make a sauce and not an omelette. So the question is, why does homemade sauce taste so much better than a packet sauce? And why does a packet sauce always work? Well, the answer is the following. The droplet size determines the mouthfeel and texture. The average size is larger and the size distribution is broader in the homemade sauce compared to the packet sauce. However, the stability of the emulsion, whether it makes a sauce or becomes an omelette, is determined by the zeta potential of the egg yolks. And the egg yolk, as we saw in the previous slide, is a very complex mixture. Now, a packet sauce uses dried egg powder from hundreds, maybe thousands of eggs. And so you're always working with a constant emulsifier system. However, in homemade sauce, you typically use a couple of eggs. The emulsifiers you get depend on what sort of eggs the chicken has laid for you. And here I show the results of 2 eggs just taken at random. And you can see that the zeta potential profile varies enormously, which shows actually you can always make a stable homemade sauce, just throw in enough vinegar. Sadly, it will be inedible. So I hope that I've been able to persuade you that zeta potential measurements can be especially useful in formulation and application of particulate suspensions. And rather than being an often underutilized, even neglected technique, zeta potential should be considered as a necessary primary particle characterization method. Thank you very much for your attention.
Well, thank you so much, David, for the excellent webinar. I found that it was super interesting, especially the very last example. We've also measured mayonnaise, something a little bit on the similar side, and we found that, hey, in the range of 10 micron is when people perceived it as yummy, high quality. And so in addition to zeta potential, I think size is also super important. I have a question that came in. May I go ahead and read the question to you? Okay.
Yeah.
So this came from the registration. So do polymer molecules have zeta potential?
Oh, yes. I mean, whenever you make a polymer, no matter what it is, basically because there's an initiator needed somehow or other to make that polymer. Forget about emulsifiers. You can make polymers emulsifier free. There has to be an initiator. That initiator could be something as simple as hydrogen peroxide, or it could be basically a persulfate acid of some sort. Okay, and that gives the polymer itself some sort of chemical as part of the structure. Now you can actually remove a lot of it by treatments. Okay, but you can do things like corona discharge. But ultimately, every surface, somewhere or other, will have some sort of fundamental charge stuck there as well. Now, again, polymer latexes we can work with in suspensions. Of course, you can't measure the zeta potential of a sheet of polymer you're using microelectrophoresis. I showed earlier that there are other techniques to be able to do that, but functionally, yes. And this is important to realize. In fact, I showed you the zeta potential of the glass sheet. And basically, that also becomes part of a formulation problem. Let's take a very simple example. Whether you store a suspension in a glass jar or you store it in Nalgene will make a difference to the shelf storage stability, because the zeta potential of the glass or the polymer inside will also impact how it interacts with the particles.
Thank you. Next question. Are there resources online where you can find a collection of Z potential versus pH for different materials?
Okay, so the answer to that one is probably not. Okay, however, what you can find if you Google the name Marek, M-A-R-E-K, Kosmulski, K-O-S-M-U-L-S-K-I, he has at least 2 books, or 1 book and 1 main review, which lists dozens and dozens of isoelectric points and gives some examples of profiles. So here's the interesting thing. Although you get an isoelectric point from the literature, the only true way of finding out the profile is to measure it yourself.
Thank you. Next question. Have you ever measured zeta potential of water-based epoxy emulsions?
Water-based epoxies used for making like fiberglass and things? Well, okay, yeah. Well, the answer to that one is yes. And the point about it is, once again, I mean, anything like that, even cationic resins are used. the fact is, if you take those materials and you basically titrate them as a function of pH, if there's any surface functionality, zeta potential will pick it up, okay? And by the way, in formulation, it's not the 99% that you know about that kills you. It's the 1% that you forgot about or didn't measure or didn't even know about, because we're talking about interfacial chemistry here. And it's what matters exactly that interface that controls it. It's not the bulk properties of it. It's what happens at the interface. And that's why it's important to do proper full physical characterization.
Thank you. Next, how to define the pH of the storage buffer in relation to zeta potential?
Pardon? How to define what?
The pH of the storage buffer.
As a storage. Yeah, well, the thing is, it depends now, again, at what the isoelectric point is that you can't store pure rutile titanium in water at pH 6. It's aggregated. So if you make it, if you make it at pH 4 and it's stable there, then it should stay. In fact, I know it will stay stable itself. You can actually make it more stable by using a dispersing agent itself. But yes, if you simply take titanium dioxide, a rutile, and just make a suspension of a pH 3, basically, but what you have to do, and I haven't got time to go on all this, but one of the things about it, I did talk about with respect to the silica, the actual development of the charge on the surface is a kinetic process. It takes some time. It's not always instantaneous. And when years ago I worked with a company called what used to be called British Titan Products, now became eventually Tioxide itself, I was shown that in those cases when they make up suspensions of titanium dioxide to measure, and they were measuring zeta potential back then, is that they made a slurry up at constant concentration because the chemical equilibrium changes with concentration of particles. Again, haven't got time to go into all this, but importantly, you make it up a constant concentration, and then you wait. And they typically would wait 24 hours before they took that sample, and they took that sample of concentrate, and then they diluted into a solution at the same pH, pH 4, or pH 4 containing whatever ions you want to put in, or pH 4 and something else, okay? So storage depends upon those solution conditions, and if you've made it as a stable, then it should stay at that. And by the way, you can measure the zeta potential, and by the way, you can also follow it with particle size, because of course, if there's aggregation taking place, then what will happen? The particles will get bigger, and there's plenty of papers in the literature just showing those studies.
Got it. Very cool. So we got quite a bit of questions that came in. What is the ideal solvent for the zeta potential measurement? Is it 0.9%
ideal solvent? Well, okay. So there's no. It's not a solvent. We're talking. What's the? There is no ideal liquid. It's the liquid that you need in order to make your product. So let me give you throw a few examples out here. In the lab, if you make measurements of distilled deionized water, forget about the pH, just in that water itself, that will bear no resemblance to a plant that uses plant water, hard water or soft water. So if you're going to do formulations and they're using in plants, get samples of water from the plant. That's one. Two is that when you're doing that, depending upon what you're doing, what dispersant or that you want to use, water is ubiquitous, is used in a huge number of suspensions in water. So it's not a question of what's the best solvent. What is important, however, is in non-aqueous systems, the presence of water in a solvent system or on the surface of the particle is what drives basically all the interfacial chemistry. And we tend to forget about this. And solvents basically do contain small amounts of water, parts per million. But what you should be doing with the solvent system, whatever you're using, is actually doing something like a Carl Fisher titration and finding out how much is there. Because even if you start with a known surface of titanium, you put it in a solvent that you buy a different batch of, or from different manufacturers, it might have different amounts of water in there. And the other point is that when we talk about putting a particle in water and talking about adding H plus or OH minus ions, protons and hydroxyl ions. In reality, what we're actually talking about is really an exchange of electrons. It's an electron donor acceptor process, not a pH change. The pH is just because we're using water. But when you put a particle in a liquid, you get a difference in this electron donor acceptor, basically equilibrium between the surface and the solution. And that dominates the ability to disperse materials. Again, Google electron donor acceptor theory. Going back to the late 60s, Fred Folks and Mohammed Labib, they go into it in great detail. And yeah, the biggest variable in making measurements in non-aqueous media is water.
Thank you. For emulsion slurry with multiple ingredients and high concentration, how to estimate needed parameters such as density and refractive index?
How to determine what? Density and refractive index?
Correct.
Well, I'm not really an expert on this one. It's density. You know, I would just be using basically a refractometer or a density meter. You know, probably based upon on ultrasonic attenuation of something. Yeah. I mean, again, I'm not a, you know.
I think there are ways to estimate, and I will send you a paper, and it's based on the weight percentage of each ingredient.
Yeah.
Thank you. Okay, so next question, how do we measure the zeta potential of dry powder, say illite? I hope I pronounced it correctly.
Pardon? A dry powder?
Correct.
Well, the zeta potential really only develops when you've got a surface of shear because you've got liquid present, okay? So you can't do a dry powder per se, although mixing a so-called dry powder will be different depending whether it is truly being dried or basically whether it has, in fact, because of the surface hydroxyls, a layer of water around it. Yeah, and certainly zeolites are used as catalysts. Okay, and their behavior can actually be quite variable depending upon even the relative humidity of using those powders. But the problem of technically, it's possible to measure a surface charge directly. It is not easy. I'm not even certain that these days. I used to know in the 1960s of a firm that sold for measuring on powders, but I don't know even if in existence anymore.
No problem. But in some, it's rare to see it in dry powder. Okay, what happened in the case of magnetic nanoparticles? And this is a multiple part question. Which solvent should I use to accurately measure PZC? And
okay, so
note that these nanoparticles tend to agglomerate
due
to dipolar
absolutely
interactions. Right.
Yeah.
Okay.
So it's interesting that the zeta potential is an average on the size of the particle, and very often you'll find that as long as not massive aggregates, then actually the zeta potential of a 25 and a 50 nanometer particle might not vary all that much. The problem with it is keeping the particles apart while you're making a measurement. Or one big advantage of using electrophoretic light scattering or phase analysis light scattering is that what you're doing with the particles is you are seriously diluting the system, okay? Which means in order for the particles to aggregate, they've got to touch each other. So the more dilute they are, the longer it takes for them to come together. So actually, if you make measurements on a very, very diluted suspension of magnetic, say, iron oxide particles, you can get measurements because modern equipment is very fast. You don't have to do multiple runs to get an average. What you do is you do many, many, many single runs and average them itself. Is that you can get quite a reproducible value, even though if you wait long enough, the particles themselves will aggregate. The problem about stabilizing these materials so they don't aggregate is typically what you need to do is you need to coat the surface with some sort of hydroxylated species like like pegylated or even honeyworks or dextrose or something like that, or, that basically gives you a steric layer. The problem with that is that when the particles are coated, the zeta potential is going to be almost zero. However, even though the zeta potential is zero, the particles are stable. So one thing you can do is to take the magnetic iron oxide and then mix it in with something like as I say, a honey or dextrose, mix it in so it absorbs on the surface, and do a measurement of zeta potential as a function of the amount of dextrose. And when you get to the point where the zeta potential goes to zero, and now you've got to do in relation to this, you've also got to look at the size, because if the size now stays constant, what you're doing is you now know absolutely you're stabilizing the particles. I've got data showing this, how you can do this, where you take a particle and coat it with a hydrophilic polymer and completely stabilize the material. So yeah, measuring those measurements can be difficult, and also applying the field. That's why phase analysis is a lot better. I haven't gone into talking about different instruments and how they measure, etc. That's something else. But if people want to know more about it, I can certainly talk offline to them. Okay.
Correct, and that's when you can certainly send questions to labinfo@horiba.com, which I'm going to send in the chat box, because I do want to honor Dr. David Fairhurst's time. A very last question is pretty practical. And just a side note that people are measuring COVID-19 coronavirus, since they have a zeta potential of minus 30 millivolts, and they use that to trap the virus in the nanopores for detection. So I thought that was kind of interesting.
Yeah. Yeah, years ago, I was working with HIV, and yeah, back in the mid 2000s, I worked for the Gates Foundation on a project for developing a vaccine, and we measured the zeta potential of HIV. Yeah, because what we were looking at is basically how to combat HIV. And it's very interesting. It's a slightly different thing, but HIV is of course transmitted sexually, and it turns out that the pH in the vaginal lumina changes, and when it changes, the zeta potential of the HIV changes. So and it was very so the fact that they're using COVID, the zeta COVID-19, way to go.
Yeah, absolutely. So then how do you know, and this will be the last question before we wrap up, how many measurements are needed to get a reliable zeta potential for a sample?
Okay. Well, the thing is, it depends upon the precision of the measurement you want. I worked in an area when we did everything manually, most of the thing, although years go by and we come to automation. The question becomes, what differences, as a rule, I consider zeta potential to have an error of no better than 5%. Okay. So the fact is that, and no matter how you make, no matter what you do, because of the broad nature of charge, it's not a defunct, it's not a single number. That's why when you measure, you get a distribution of charge itself there, and you overlay it. And like everything else, the broader the distribution, the more problems you might have when you're mixing materials, the narrower the better itself. So it comes down to two things. One, what precision do you actually want, and how long do you want to spend? Modern instruments can give you quite a lot of measurements to give you a lot of confidence in the measurement itself. But as I say, my rule of thumb is, if I get a sample of material that's an unknown, what I do is I mix it all up, and then I take a sample from the top, the middle, and the bottom, and I make between 3 and 5 measurements on each of them. Okay.
Perfect. That's really generally the rule of thumb that we follow as well with laser diffraction and particle size analysis. Okay, so great. That was really fun. My apology for not being able to follow through every single question, but you are more than welcome to email us at labinfo@horiba.com, and we will address the remaining questions offline as well. Please don't hesitate to give us any questions, feedback that you may have. David, do you have anything else to add before we wrap up?
No, thank you very much, and I hope the attendees at least got some information which is useful to them.
Absolutely. Well, for now, have a great day, and we'll see you at one or more of our future webinars. Thank you, everyone.
Thank you.
Thank you.
Bye-bye.
Bye-bye.